Good morning, everybody. I'm Nadir from TransSolar. Thank you, Philippe and Klaas, for inviting us. We have worked together, as Philippe already introduced. I've also worked a little bit with Klaas on a project that's in construction currently. So I'm very happy to be here and actually meet you in person. It was mostly through Skype, actually, that we had worked on various competitions. I was not going to give a formal corporate introduction into what TransSolar is, but yesterday I've been actually asked whether we would sell solar panels. So probably we should. We own the transsolar.com domain name, and maybe we would make more money with selling solar panels. Let me just, for 2 minutes, talk about what TransSolar is actually doing. So we basically help architects and advise them on climate responsive design. This has to do with energy concepts. It has to do with understanding the interaction of buildings, cities, urban developments, with environmental forces like the sun, winds. It has to do, as I said, with energy concepts, thinking about climate, microclimate on small scale, larger scale. And we are roughly 50 engineers and distributed over 4 offices. Originally from Germany, in Stuttgart. You can probably hear it by my accent. We have an office in Munich. I used to work in the New York office for a few years, and we have an office in Paris. But please do not ask me why there's no one sitting there. They just gave me this picture, maybe. I don't know, must have been August or who in here is French? Hands up before I make too many jokes. Okay, great. Just to give you an overview over an array of projects that we have been involved in. Some of you may know some of them. Very small projects, like that little building at the bottom. I have designed together with Renzo Piano for Vitra, 6 square meters only. And the idea is that you can do everything in this. It collects its own rainwater, heats it up, produces its own electricity. You can sleep in it, you can work in it, you can, it has a little kitchen, a bed, you name it. So, all on 6 square meters. We have built several prototypes, but the idea is that Vitra is going into series with this product. They typically build chairs, so they consider this kind of a furniture, rather large furniture, of course. So from very small projects to very big ones, Mazda City, most of you have heard of that. Kind of controversial, and I'm not going to talk about this, but really the questions that we addressed was, how do the winds go past or through the city? Questions that have to do with street width, urban layout, building height, orientation, solar radiation hitting various aspects of the facades, and so on. Interaction with daylight, and of course also how can you produce in that city sufficient energy and integrate that energy production to operate such a city. So from very small to very large. At the top you see a rather, let's say, humble project, a school, passively operated school in Damascus that is drawing fresh air through some courtyards with evaporative cooling and so forth through the ground, driven through some solar chimneys. So there's no energy used for this kind of building operation. And we learn actually quite a lot from those kind of passive strategies, try to project them onto more commercial projects, such as in the bottom left you see a project in Canada. I was talking about this yesterday. Probably the most energy efficient high-rise in Northern America. It's in Winnipeg, so very harsh temperature differences from -30 to +30, even warmer actually. So similar strategies, solar chimney, atria, natural ventilation, intelligent way of shading the building and so forth. It has a double facade, so you name it. It's kind of a haven for a climate engineer. But those buildings, you know, while they are of course very different in budget, are very much related to one another. Place de la République, we're here in Paris, so if anyone knows that place, we have been involved with TVK and, you know, thinking about materials and also winds, water, solar exposure and the comfort on people. I will talk about comfort today a little bit more. And then some more recent projects, one that is just upstate of New York, well, Connecticut actually, and the Iowa School of Arts with Stephen Hall. This building down here is with Sana. Well, you know, while we have only a very small stake on every project, we are involved in a lot of projects, but not enough. We kind of have a mission, you know, to make buildings a bit more sustainable and more energy efficient. And because we can be involved in only so few projects, rather than, you know, spreading the message into the world, we have decided, okay, let's try to get what we call the so-called majority world to Transolar, and founded the Transolar, what we call the Transolar Academy. So it's basically a scholarship for 6 to 7 young engineers, architects that stay with us from all over the world. They come to us every year for a whole year, fully funded scholarship. So this year we have a guy from China, a girl from Cuba, Greece, Argentina, South Korea, Syria, Zimbabwe, Vietnam and India, and it's very inspiring to work with those people. I just had a session with them last week about their future, and whenever I have a philosophical question, for instance about models and tools, I have very interesting discussions with them. So not only they have very different cultural backgrounds, but also different backgrounds in terms of their education. So some of them are engineers, others architects. If I look around here, any engineers in here that are, well, who is not an architect? Oh, quite a lot. And so the rest, architects, hands up. Okay, just trying, you know, to relate a little bit. Get to know you. I only came actually last night, so I missed the last 3 days of the symposium. Who likes Titanic, the film? No one? No? Sorry, just trying to break the ice. What's your favorite movie? What? Pulp Fiction. Okay. So, engineers and architects. I myself, I'm an aerospace engineer. You were talking about those people. It's interesting that architects like working with, I don't know, you know, static people who are into static things like flying objects too. So, but those of you who went through engineering school might also had to do what I had to do, which is working in a workshop actually for some time. So they send you to a workshop, so you learn how to work with metal, you know, drilling holes, sawing, metal turning, welding, and all those kind of things. And so when you're in that workshop, there are some people, some mechanics, they're very skilled in their tools. They have years of experience. But then in the hierarchy of such a workshop, you also have the people who are one level higher. They actually not only hone the skill of using a tool, but they also make their own tools. So that in German, they call them, if I literally translate it, they're called tool makers. So you may know that you're an engineer and an architect at the same time. They are also here. So those guys, you know, they are typically paid double the amount. So, and I have those discussions with our academy group a lot. You know, to what extent do we use tools, and when is the time to actually create your own tool in order to address certain questions? So, you know, we think a lot about tools, and I'm now a little bit more senior to them, so they ask me a lot, so, you know, which tool to use, which tool to learn, and so forth. So I just made a list of the various tools that we use at TransSolar. Sorry, this is white on black. I was hoping everybody would be wearing black that day. There are also some architects and engineers. So, you know, if it's an array of tools, and walking around yesterday, I saw some very fantastic tool-making strategies and projects. So rather than just using tools, I think there's an interesting prospect of collaboration here for new tools. I was also very interested in what you have shown, Jane, because you not only showed computational models, but also physical models. And TransSolar is heavily involved in also, you know, testing, creating mock-ups, trying to understand really the physics on a more, you know, human scale. I guess that's also the title of the symposium today. So, you know, often we ask ourselves, should we do a physical model or a virtual model? I personally have a more virtual background. In fact, the world of aerodynamicists is divided into physical and virtual, and you rarely find someone who is making a living with both, you know, wind tunnel and working with the computer. You know, so with those guys, we have the discussions about what models are appropriate. And probably we have kind of agreed, at least in the world of aerodynamics, that there's some coexistence between computational tools and people who pursue computational tools as opposed to virtual tools. So this is an example just for like a daylighting study in a museum. Here a museum in Houston with Stephen Hall. And of course, you cannot replace physical model with only computational consideration. So in particular for that museum, we are building a 50% mock-up. You know, but this is early days, just holding a model against the window, learning from the very simple interaction with the sun. So finally, I can show you a real photo of, you know, what you see on the left, a model. I've been showing this for the last 3 years, only the left picture, but last week the Saryadyo Park in Moscow has been opened. A project with Charles Renfro from Deleuze-Scofidio and Renfro. It's a park similar to Tianjin that you just presented. We thought about the climate a lot, how people will interact with the environment. Moscow, of course, has a very harsh climate, especially in winter. So we wanted to play with this, create super climates, anti-climates. There's an ice cave actually operating the entire year. And the vision of DSNR was really that, you know, there's a hill, and on top of that hill, we have a shelter. It's open, accessible all year round, and even if it feels cold outside, it feels warmer on top of that hill. We know warmer arises. I will talk about this a little bit later. But to get from, you know, that vision, that notion, that model, that mental, let's say, model, to a real, a real building, a lot of models probably have to happen in between. And that raises really the question, what is a good model? And yesterday I just Googled this actually, what is a good model? And Google must know that I'm in Paris. So they showed me something like this, and I thought it's a fantastic image. Because it actually reveals to me what I think is, you know, one of the aspects of what a good model is. It has to do with simplicity. Simplicity as in simple, as in plain, as in reduced complexity. So these models, you know, look all pretty much similar in order not to distract the attention from what you're actually really interested in, which is, in this case, a beautiful cow patterned night robe. So I want to talk a little bit about simplicity and in the context of different projects. So this is the plan of Saryadyo Park. On the left, you cannot see, it's the Kremlin. So it's very, very central in Moscow. If you ever have the chance to visit, already on opening day it was treated a little bit controversial. Of course, it's yeah, you know, but it's an outside park, a park for the people. But of course, from an urban point of view, it's also very brave to actually build something like this. But this is a rendering. So, you know, we looked at the winds, the prevailing winds mostly coming from the southwest, but also west and the south. And you can see here on the right-hand side this huge canopy, around 15,000 square feet. On top of a hill, under that hill, there's a Philharmonic. Under that Philharmonic, in fact, under the entire park lies a very, very big secret. No one knows what's under there, me neither. Anyway, so there's a topography, and we try to understand really, so, you know, how will the winds interact with that topography? That was kind of the original idea. So imagine you're outside, it's fairly cold, maybe minus 5 degrees. You know, you walk up that hill, the sun traps solar, the canopy traps that solar energy under a glass crust, like a greenhouse basically. And as air is rising up, you know, in the shape of the bubble, that warm air cannot escape, unless, of course, we have wind taking that away. So, you know, the key was really accessibility, not to close this off, to have this an open kind of structure. Originally, we intended to also find some waste heat from the Philharmonic to, you know, maybe also introduce into that space. But right now, this is only passively heated. So the architects came up with all kinds of different shapes for that hill, shapes for the canopy, and asked me, you know, what's really the best to achieve our target of having a wind-sheltered, open greenhouse. So we did what you then always do. You do some CFD. It takes for each of these, you know, a couple of weeks of a highly paid CFD engineer, and then you look at the results, and really you didn't learn much from this. So, you know, what does this mean? You know, it's maybe the simple geometry versus the bubble vault or the barrel vault. How should we interpret these results? How can we develop them further? Especially if the wind turns a little bit, even if we could make sense of this, even when the wind turns slightly, the situation may look totally different. So rather than, you know, sticking to this complex idea of we need to solve a certain future reality, we ask ourselves, okay, can we reduce that complex model to a more simple approach of addressing such a canopy? And we did that by introducing a, you know, cartoon-like hill to begin with. So if you ask a child to draw a hill, you know, how would this look like? And then we started by just defining a canopy that's parallel to that hill, and then to come up with like a set of parameters, 3 only, not more, to understand really the relationship between such a canopy and a cartoon-like hill. So, you know, probably the edge is relevant, where the wind could enter, but maybe also the top of the hill where the wind could disperse, and maybe somewhere in between. So, you know, it's a strategic decision to reduce the complexity of such a model into something that not only we can handle, but also learn something from it. You know, and then you come up with certain rules, let's say, design rules, rather than facts, that the architects would be using to, you know, shape their canopy. And this was last weekend. That's the final shape. There was no wind on that day, unfortunately. There are also some accidents happening, so you can talk to the architects about that chimney poking through that canopy. The architects of you must feel sorry for this happening, but that's part of the design process. So, you know, and only then, actually, after understanding the dynamics of the wind, after feeling comfortable with what's happening to the wind, we ask ourselves, what does that actually mean for people finding themselves under that canopy. You know, of course, has also to do with other factors: humidity, sun, what people are wearing. The fact that they're actually climbing up a hill will make them feel even a little bit warmer. You know, and then we take all that information into one, let's say, human thermal comfort model, and try to understand what the perceived temperatures under such a space could possibly be. So the purple colors, that's more outside, whereas you then have the elevated temperatures under the sheltered space. Simplicity can also be found, as I think, in this model. It's a model. It's an installation that we've done with a Japanese architect and together with Sanaa in 2010 at the Biennale. The idea was to create an indoor cloud. And little did we know at that time that what we were going to create was actually not a cloud, but, as I think, a model of a cloud. And I want to show you why I think that is the case. So, normal clouds, okay, the ones that you fly through in a plane, are of course three-dimensional objects. So they have a complexity that, you know, meteorologists like to refer to in like cryptic coding using complex Latin categorizations, let's say, in order to assign them to different weather phenomena. It has to do with not only humidity, but also pressure, air movement, winds. We all know how difficult it is actually to predict the weather, let alone to model it. So in that sense, this is what you see here is a simplification in the sense that it's actually only a one-dimensional cloud, in the sense that the atmosphere changes only as you go up. So the idea behind that is you still have a warm and humid layer of air, and you have a cold layer of air, and as they interact with one another, droplets starts to condensate and find themselves balancing in a certain layer. And it has also a little bit to do with the fact that humid air rises. Humid air is actually lighter than is lighter than dry air. I will talk about this also a little bit later. And yeah, so it's a very much a reduced static model actually of a cloud. You also know that clouds are very transient phenomena, so they change continuously. The idea here was really to have a stable layer that's floating, a stable humid layer that's floating between two rather dry layers. Here you can see an image that we took with an infrared camera. You can really see the temperature difference between the ground and the top. Don't get distracted by the 66. This is actually the light. So we had a temperature difference of roughly 15 degrees. And in that kind of atmosphere, the humidity will actually balance in the middle of the space. So, as I would say, a physical model of physical representation of something that we know from reality. Here, a virtual context. That's the Academy Museum of Motion Pictures, currently in design with Renzo Piano. Actually, they already started construction. Parts of that is being renovated. That round bubble is being, that's a new build. It's actually a movie theater. At the bottom and at the top, it's somehow similar to the park in Zariade, an outdoorish, let's say, buffer space that's protecting people from rain and wind, and maybe from cold times, but it's not fully enclosed. And that brings me a little bit to what I think is the second aspect of what makes a good model, actually, which is asking the right question. And the right question here is probably not, how can I build an enclosure, a fully enclosed space in order to satisfy the needs for people, but how can I actually achieve thermal comfort for people? It not necessarily has to be a fully enclosed building. Actually, I keep being asked for the non-building. A lot of architects like the idea of a no building or zero building. Or so those are the aspects that are really important to understand what makes a person feel comfortable in a certain environment. Whether that's outside or inside does actually not matter so much. I actually think if a person can relate to the outside, also there is a mental shift happening that will relax people more and adapt them more to, let's say, a wider range of environmental parameters. So, but it's not just wind; it's also something most people do not know. It's, for instance, the temperature of the sky that's surrounding you. The sky has a temperature. It's actually the temperature of the atmosphere, but you can think of this as a surface, typically colder than our air temperature. And of course, air movement. You know all of this from your own experience. So also here we did some CFD modeling. Not only CFD modeling, different models. Again, simplified, reduced models in order to understand the interaction here with the space. In order to really understand the relevance of the key question, which is thermal comfort. Not how big does the chiller have to be. What is it actually? What kind of comfort do we want to achieve? And can we question that comfort actually? So to come back to the cloud, what are the relevant questions for a cloud? What can we gain from a physical model such as a cloud? It certainly has to do with perspective. That was the idea, to give people the experience to find themselves under the cloud, in between the cloud and on top of the cloud. So here you see Tetsuo Kondo, the designer of the beautiful ramp that allows for that experience. So not just experience in terms of visual experience of seeing the cloud, but also feeling what that means to be in these different atmospheres. So here you just see some impressions from underneath and from above. You can see that we had to temper a little bit with the historic building and close the gap off if you know the Arsenale building in Venice. And because we were interested in that concept of perspective, being below, in between and above, we at some point realized we want to take that question a little bit further, because actually there's very few situations where you can see all those three moments at the same time, because you're either under the cloud, you're in between the cloud, or you're above the cloud. So you know this from probably when you're, let's say, in the mountains, you can probably experience also seeing all three layers of cloud as the cloud is farther apart. So I think this is an interesting moment that you experience here in Tokyo, where we did, let's say, an alteration of that installation, where it's enclosed in a box, where from outside you can actually see all those three layers at the same time. And again, of course, you would be able to experience these different atmospheres as you walk through. So, sometimes I'm being asked, why do you guys do clouds? What does that have to do with architecture? So here's just the list if you're interested in it. My third point, why I think, or third aspect of what I think is an important, property of a good model. It should allow you to discover something, of course. So we have now asked the right questions. Hopefully we'll find answers to those questions. Speaking about the cloud, here you see a art school in Houston that we're designing together with Stephen Hall. Houston, very humid, of course. So there were certainly lessons we could take from that cloud into the Houston climate to understand really the thermodynamics of humid air moving. By the way, the school has been just slightly damaged in construction process, but I think they're on track. Talking about Harvey, I will also talk about hurricanes later. So this is a CFD that takes really everything into account, not everything, but quite a lot of the dynamics of air, humidity, radiation, of course momentum, turbulence, and so forth. And the question was really, what happens if a student opens a window and humid air will enter that space? Will that cold floor, it actually has radiant cooling in the floor, in a humid climate, will we have condensation because the humidity is getting in touch somehow with that cold floor? And that CFD kind of shows that the red, that's the the warm humid air, is really rising because of the humidity, not only because of the heat. Humid air really is lighter than dry air, is rising and can then be extracted, naturally or mechanically. Doesn't really matter, but would not get in touch with the floor. So one example for discovery. Another installation, interaction with humidity, is the Lightscapes installation that Matthias Schuler from Transolar has done last year at the Biennial. Actually, some of you might have seen it. A lot of lessons learned from how light is being made visible, basically through humidity. Also about the different distribution of light in space. They've done a lot of experiment, and this is actually a model in itself for the Louvre Abu Dhabi that's just about to be finished, I think. Here with your lensman, countryman, architect Jean Nouvel, and the client. We built a one-to-one mock-up, actually. A huge mock-up just to understand that effect of the rain, that spectacular effect of the rain of light in interaction with humidity and also dirt, of course. So this is a rendering. So, and certainly there were a lot of things to discover in our museum for motion pictures in Los Angeles about interaction between winds. This is actually now a thermal model. Originally, we had excluded the thermal component in that model, but you can see here very nicely the stratification, how cold air is actually entering, finding itself at the level of people, whereas warm air is being extracted a little bit more away. That brings me to my last point of what I think makes a good model. I think there's always, not always, but I like it if there's a moment of surprise in the process of going for discovery. And so some surprising effects we saw here actually in that computational analysis, that when the wind is somehow tangential to this opening of that buffer space, you have somehow some hurricane developing inside the space. Whether that's good or not, that's a different question. In summer, probably it's nice. Okay, you could create some. You could maybe even design the installation according to this little vortex that you see here. In winter, probably you want to protect yourself from it, by maybe strategically placing objects into that hurricane. And a similar effect of surprise we also experienced in the Cloudscapes installation. During one of our tests, a group of kids was running in a circle, like they were holding hands and running around, and you could see how the air would start swirling around, and a negative pressure would form in the middle, and the cloud would, like a tornado, basically come down, and remain there maybe for half a minute or so, and then slowly, stabilize itself and go back up. So it's those moments of surprises that initially you feel you don't want to see that, because it questions you know, the way you understood a certain situation beforehand. But I also think that it's exactly, you know, these moments that allow you to go a little bit further and actually learn something about the matter at hand. So, just to summarize, basically, this is what I think makes a good model. Simplicity, relevance, addressing the right questions, discovery, and ideally on the path to that, you know, some surprising and inspiring moment, and probably a right balance of all of these, you know, will probably make a good story for a good model. We all know that, you know, there are beautiful models, there are beautiful stories we like to tell. It's almost like a movie, you know. So there are bad movies and there are good movies. And you know, what those movies probably have in common is, was that my time? I'm pretty much done. So what those movies have in common is probably some form of evolution, catharsis, but also progress. So, you know, I think if that balance is right between those, you know, let's say pillars or dimensions of what I think makes a good model, we're able to progress, even if it's just a little step. Some people may call it, you know, evolution, others may call it transformation or involution. And yeah, with these words, I would like to say thank you.